All right, hi. So that was for third period. You asked to have rap in the video, and I really can't do that unless I am alone in a car. So yeah, that's as close as we're going to get. So welcome to the third little section of this video, and we're going to work example 4 now. So this one has a really cool looking picture, and I was just thinking as I was getting this set up to do this next part about how to get you to understand to using your calculator if you're a little nervous about it. And when you go into the window for your settings for your making your graph and you're in polar mode, mess around with the theta step. If you set the theta step small, like 0.01, then the graphing of this will go more slowly and you can watch how the curve comes out like this and then comes down like this and then comes around to do this third petal of the rose, okay? And so in case that's something that's tricky to you, certainly feel free to make use of the technology that way. So this question asks us, first of all, just to go ahead and figure out the area with our bounds of being 0 and 2 pi. And then we'll, after we do the calculation of this, we'll talk again about the picture and what we actually just might have found. So 0 to 2 pi, and then 1/2 theta r squared. So that would be, here's our r, 1/2 theta r squared, or yeah, theta r squared d theta. I just said 1/2 theta r squared d theta, didn't I? That's why I was like, that didn't sound right. 1/2 r squared d theta. Sorry about that. Okay, so I hope I didn't do that earlier. I never really have the courage to go back and listen to the whole video. So if you guys find mistakes, feel free to let me know and certainly let your classmates know if I have a misspoken moment that I didn't catch. Okay, so a little bit of tidying up gives us that. And then we need to use our famous identities, okay? So we're going to get, I think I can squeeze it in right here. We're going to have a 0 to pi, and the identity is going to give us 1 minus cosine 6 theta, since it's double the angle. And then we'll have a 2, but we already have this 2. Right, so those are going to go away. And d theta. Okay, so this isn't that bad of an integral. We will get theta. Have to insert a 6 and balance it with a 1/6. And have our bounds. And when you substitute all that in, you get 2 pi. Super, okay? Now, question, is that the actual area of the rose? Well, in order to know that, we have to know when we come back to this pole, right? And do we come back? I'm not really sure, right? So how do I end up figuring out when we go back to the pole? Well, we let our radius be 0, or r value be 0. And so the solutions to this would be 3 theta, because you divide by 2, you still have 0. So 3 theta, and then the places where sine would equal 0 are 0, and then pi, and then 2 pi, so the multiples of pi. And then if you divide everything by 3, you would say, well, theta would have to equal the multiples of pi over 3. Okay? And so it seems to me, and playing around with your calculator will verify this for you, that this loop happens from 0 to pi over 3. And then from there, pi over 3 to 2 pi over 3 is this loop. And then 2 pi over 3 back to here is the third loop. So each loop is figured out by a pi over 3 section, so to speak, starting from 0. And so this actual area of the rose is, yeah, no, it's not going to be 2 pi, because 2 pi is actually 6 petals worth. And we have a graph that has 3 petals. So to get just 1 petal, I'm going to change this to have bounds of 0 and pi over 3 on my formula. Okay, and when you do that, I mean, it's just a matter of going back and making those bounds be right. You end up getting pi over 3. And you can kind of see that logically as well, since we got 2 pi as our answer before. And so that means that 1 full graph with the 3 petals, using the idea of symmetry, is going to be 3 times that 1 petal, or pi. Okay, so if 2 pi is 6 petals, certainly it should make sense that 3 petals is pi. All right, I hope that makes sense. Again, if not, email me. Okay, here we are, example 5, and example 5 is the most interesting example. You can see that I don't have a picture yet of what this graph looks like, but I am going to just follow the directions at the beginning, which say to try finding the area with bounds of 0 and 2 pi. So here's our setup, and just to have the experience, I'd like you to practice doing this integral, evaluating this integral with your calculator. Now, you might be in polar mode right now because you've been looking at polar graphs. But in order to evaluate this, you're going to go back and just use your fn int feature, which means that you need to go back into rectangular, and then everywhere you see a theta here, you're going to use the x. It's a variable. It doesn't matter to the calculator that the context of this problem is polar. It's just an evaluation. You're still doing the same anti-differentiation. So the fact that it came from a polar context doesn't matter as far as the mathematics. So go back into rectangular mode, type this guy in, use fn int, and then come back in a second and see if you have the same result as I do. Okay, so pause the lesson for a second and take care of that. Okay, you can see my decimal on the screen, and so hopefully we match on that. And then if you do want to go back into polar mode, or if you want to just try plotting some points, it's very tedious, but it is possible to do. You can try plotting the graph to see what it actually is, so we have some sense of what's happening. Now, if you look at the equation, if theta is 0, sine of 0 is 0, so that second term is going to go away. So this graph actually starts out here, 2 rings out at 0, and then it makes this big arc. It goes up to maybe like, yeah, I'd have to go up to 6. So 1, 2, 3, 4, 5, 6. It goes up to about here on the polar graphing paper. And then it would have some symmetry come back over here. So it's going to have this big, tall, loopy thing that comes up like this. And that's where we are at pi. And then it comes in and it does this interesting thing because of the signs, SIGN kind of signs, that you get this inner loop like that before you come back to the beginning. So this is definitely more challenging in terms of finding the area. Okay, so what we've actually done, and this is a really key idea. I didn't realize how key this was until I'd done a lot of these problems myself. But if you think about this point as being your pole, okay, then as you sweep through the polar area, think about all those wedges coming out. Think about like just drawing radii. Okay, so do you see I'm finding as theta would change through this region, I'm finding the area of all of that. And then it gets really tight in here, but then it goes through the loop. And so then I am finding the area of this part, which already was included in the yellow. And then I'm going to be coming back out here and finding this little nugget at the bottom down here, this part. Okay, that's kind of hard to do because that was a pretty small picture. So here's a bigger picture. But I hope you understand that, like, when we went 0 to 2 pi, we actually, like I have a spot here. I don't know how to do this for sure. How to visually describe this. Sorry, technical glitches with my being, almost 50. Hold on a sec. Okay, sorry about that. I just lost a few things. Okay, so we went from 0 to 2 pi, and we were really finding, like it says here for C, describe visually what we just found. I don't know how to describe it in words, but what we found was this whole shape. And in addition to that, we found this shape. But this shape that I colored in blue right now is contained in the bigger one. So these are overlapping. So it's like this part got counted twice. And that very well might not be what we want. I mean, maybe it is. But usually that's not the case, okay? Usually you want to find some particular region. Oftentimes in AP questions, it's shaded regions. So let's just focus now, like how could we just get the inner loop part? How would we know this section's area, right? If the wedges were just coming out like this. Well, again, you start at this pole, and then you're going out through the shape, and you come back to when you're at the pole again, okay? So you need to figure out, when are we at the pole? Well, the way that we find out when we're at the pole is to solve this equation. So this is what the values of theta that give a sine value of negative a half, right? Subtract the 2, divide by 4. And so that's going to be at 7 pi over 6 and 11 pi over 6, if we're looking at between 0 and 2 pi for the whole thing, okay? So if we wanted to get the integral of just the inner loop, we would set it up to be just those bounds. One half r squared d theta, okay? And then part E, this is a little bit confusing, I think, okay? Just got to really think about what you're doing. How could you write an integral to get the area of the outer loop, not including the inner loop, okay? So if we went 0 to 2 pi, we would get everything, right? That was that sort of upside down tomato is what it looks like to me. Like a tomato like just turned over. I was just at a gardening thing today. Maybe I've, vegetables on the brain. So I've got 1/2 and then 2 plus r sine theta squared. And that's going to give me, actually starting from right here, right, and going all through this shape, and then it's going to go through that inner part, and then it's going to come back out, okay? So this part was counted twice, okay? I only want to count it once. So I would have to subtract that inner part. So that would give me just the shape without that inner loop included. Okay, so if I were to just subtract, oops, lost my pen. If I were just to subtract this part, this, okay, then what I have is this first section is giving me the outside shape, including this twice, right? That part was included both in the sweeping around the first time, right? As we went, we started from here. That is coloring in the middle part, and now that middle part gets colored in a second time. So if I just subtract it just like this, I have taken away the overlapping part. And so the shape, the amount that I would get, like if I just did all of this, is for this shape. Everything counted once. If I mean I want the area of this, and I want that loop not to be included, I want this part in the middle to be hollow, then I have to subtract that twice. So it depends really how, this question I think is a little ambiguous. How could you write an integral to get the area of the outer loop, not including the inner loop? So do we mean this with a hollow thing there? If we do, we need to have a 2 here. If we mean we just want this shape with everything counted exactly once, then just subtracting it with a 1 here would be fine. Now, the good news is, in case you're worried about ambiguity, is that AP writers are better writers than I am, and so they would have a picture for you usually that's shaded. If ever you're confused, like within our classroom, about what a particular phrase means, then you just ask. All right? We can be happy. We finished the videos. Good job, guys. Thanks a lot. Happy problem solving.